All right, this is section 5.9, beam deflection. Again, we've touched on this topic a number of times in our courses together, starting in Strength of Materials, where we use the formulas from the back of that textbook, which you'll see where really came from the AISC steel manual. Then in 311, we had the pleasure of learning all the different a number of different other methods of calculating deflection using double integration, conjugate beam, and everybody's favorite moment area theorems. Okay, so certainly there's plenty of ways of calculating deflection. Oh yeah, and then you could still use the stupid box, right? The computer. So there's plenty of ways of calculating deflection, but in practice, you'll find you'll probably end up remembering the formulas of the loading types you see very frequently, such as distributed load and concentrated loads at midspan. And again, deflection is, I wouldn't say a guess, but it certainly is a educated approximation. It's never exact. Okay, we can calculate it and get some exact looking numbers, but the reality is the actual behavior in the field is going to be different to some degree, but it's better than nothing. And we can certainly use it for our regular day-to-day work. Okay, so deflection is really serviceability. Okay, remember we always talk about structures must serve two masters, one being strength, the other being serviceability. So deflection is definitely a serviceability issue. Let me change my pen color here. Definitely serviceability. Deflection is serviceability, and there are other things that fall into the serviceability characteristic. Thing to remember about serviceability is the word service, okay, meaning service loads. Okay, so we always use service load values when checking anything for a serviceability issue, such as deflection, drift, ponding, vibration. Okay, so anyway, there's lots more than just deflection regarding serviceability. All right, so primarily what we've been dealing with is vertical deflection of beams, okay, but you can have a serviceability condition on horizontal drift of frames, right? As I push on a frame, there's a limit of what we call H, maybe over 400, and H being the height of the structure. So there are other deflection conditions that we check in our work, okay? But let's focus on beams still, same as we did in strength of materials. So, everything goes back to deflection being span over a number, okay? As I've said a number of times, the best way to communicate deflection is in terms of a ratio, not so much the actual value, okay? So we'll review that, and then we'll also review table 3-3 in the steel manual, which is what we call the IX table. It's various wide flange shapes ordered in increasing moment of inertia values so that you can efficiently select a beam size that has a moment of inertia greater than what you need to satisfy your deflection. Okay. All right. Again, serviceability, it's the second condition that we have to meet in addition to strength. Everything we've talked about so far, nominal moment, nominal shear, nominal axial strength, has all been strength values. We're now looking at serviceability, and again, primarily vertical deflection. Okay. We do have vibration issues. There's plenty of research out there that tries to establish how to get vibration into acceptable levels that are tolerable by human occupants. Okay, again, sitting in an office in a high rise somewhere, you may experience vibration every once in a while. Sitting on the Market Street Bridge, waiting for the light to change, heading north to campus, that bridge definitely vibrates quite a bit. I don't know if it's within acceptable tolerances. I'm assuming it is. But again, what bothers me personally from a vibration standpoint may be different than what bothers another person. So it's a tough one to convince somebody what you're experiencing is within acceptable tolerances. Okay. Deflection certainly has an impact on interior finishes, doors and windows, or everybody's plastered ceilings. Has anybody ever seen a plastered ceiling? You might in some historical facilities, but I doubt many of the buildings we use day to day have plastered ceilings. But if things deflect too much or drift too much, you could crack walls, drywall, you could crack tile on the floor, you could crack windows. So again, it's an issue. It's not going to cause a disaster, but it's certainly going to make somebody not happy if windows start cracking and the facility doesn't, look the way it once did. Okay. All right. So again, just a reminder, service loads, typically part of the building code, not the AISC specification. And remember, owners, can override. Okay, they can make more stringent serviceability conditions, right? So you have to meet the minimum according to ASCE 7, but an owner could say, "Hey, I want less vibration or less deflection." Okay. All right, so here we are. Deflection, pretty common loading, uniformly distributed load, 5W to the fourth over 384 EI. Okay. And this number comes from, or this equation, I should say, comes from AISC manual. Okay. So you see here is our 5WL to the fourth over 384 EI for delta max at center, and typically deflection is going to be maximum near the center of the span. Okay. Another one that you use quite often would be concentrated load at the middle, PL cubed over 48 EI. Again, you got to use your judgment. If my load isn't at the center line, maybe I just put it at the center line for my deflection check. If it doesn't control, I'm good. If it starts to look like it's controlling, then maybe you want to do a more accurate analysis. Okay. But sometimes you take those shortcuts, if you will. If you have, this condition, if you look here at this, all right, delta max, much more involved formula, but is it worth it if this delta max is satisfied? If you check PL cubed over 48 EI and it works, why worry about the actual deflection? Okay. So again, these types of things we can calculate, right? So again, this is a loading diagram. I grabbed out of the textbook, has a uniform load. Again, it doesn't tell me what type of loading it is, right? It doesn't tell me if it's dead, live, or a combination of it, but I know a deflection, right? I can take, deflection at the center line of the uniform load, right? Again, it's 5WL to the fourth over 384 EI. And if I leave W and L as part of the equation, right, I know E is 29,000. And again, I know I is going to vary. So I want to keep I, W, and L as variables. Then, as my loading changes, or my beam size changes, or my span changes, I can just use this formula, right? So again, if I take 5 times W, and remember W is typically in kips per foot, so I want to take and change that from kips per foot to kips per inch. So I'm going to I want to get 1 foot on the top, 12 inches on the bottom. Again, that's going to be the same as, this conversion, okay? And then span is easy, right? L times 12 to the 4th, okay, all over 384 EI, okay? And if you take that and you end up with a small fraction, right? You end up with, let me see, what do I get? 1288. You end up with, 0.0008 showing in your calculator, okay, times WL to the 4th over I. So what I would do is I would just hit the inverse, 1 over X, and that equals WL to the 4th over 1288.88 I. That's a much more recognizable or usable number, right? So I would kind of store this and keep this handy on a sheet or in my, notes that I use for day-to-day operation. And anytime I have steel beams, right, because E is 29,000, exhibiting or being subjected to uniform load, I can use WL to the 4th over 1288 I, okay? And I can do the same for my P load at the center line, right? I know that load from the back of the book or the steel manual is PL cubed over 48 EI. And again, keep P and L in there, but I want to convert L to inches, and then 48, 29,000 I. And again, I end up with doing it the same way, PL cubed over 805.55 I. Right, so again, anytime L or P changes or I changes, I can calculate that deflection due to the concentrated load at center line using PL cubed over 805.55 I. Okay, again, I'll use that as an example. I won't take time to do the example now, but that's pretty much the calculations you're going to need. Okay, so what do we compare that deflection to? We compare that deflection to a limit, right? And we typically think in terms of span over a number, right? So certainly L over 360 is more stringent than L over 180. Okay, L over 240 is less deflection than L over 120. And notice it has maximum live load deflection. So typically we are always checking live load. And then here is dead plus live, often referred to as total load deflection if all we have is dead plus live. But that's a pretty common combination we have to check. Again, think of live, that's people, right? So when the people are in the building, that's when you want to check the deflection, because they're going to be the ones that detect it. Okay, so again, if we think of those limits, all right, if I think delta live load for this case, again, it's 30 feet, so it's I want to change it to inches per foot, okay, and I divide it by 360, that means I can end up with a 1 inch max deflection, okay, and that would be for this case. If it was delta dead plus live, it would be L over 240, same process, and we end up with 1.5 inches max, okay? So again, think about how it works. Once we put dead load on, the structure's deformed, it's not going to deform anymore. Then we impose live load on it, and so the live load would cause an additional 1 inch of deflection, but the maximum overall deflection would be 1.5 limit, okay? So we always want to talk in terms of ratios, right? So if I end up in this case, if I have a calculated live load deflection, and it turns out to be 0.75 inches. I know that's less than 1, so therefore it's okay. But, you know, let's say, and I want to report that in terms of L over a number, right? I take 0.75 inches. Again, span is in feet times 12 to get in inches. And then divided by my number. So the number in this case is going to be 360 divided by 3/4. So this is equivalent to L over 480, which is definitely better than L over 360. Okay, so you got to be familiar with that type of maneuvering of the numbers. Okay, in addition to deflection, other types of serviceability things are ponding. Okay, again, ponding is when a structure can't shed the water on the roof quick enough. And again, was it a ponding failure, or was it a failure that the drains were blocked up by all these leaves, right? But apparently at some point, right, this whole area, right, was filled up with water, right? There was water in there, and eventually it collapsed and went down into the the deli, right? So anyways, you know, ponding can cause that if the roof isn't stiff enough to prevent a dip from occurring. Certainly, clogged drains will cause that for sure, especially when you have this parapet, right? We could potentially have a foot of water sitting on top of this thing, okay? So anyways, details. But ponding is covered in the steel manual. Again, it's an appendices, Appendix 2. Again, I'm not going to go through this in detail, but you can see it's a function of spans and moments of inertia. Okay, so again, lots to keep learning in this field. Okay, so I think that's it. I mean, there's also lots of other stuff, but I think that's enough to make you dangerous. So if you have questions, please feel free to reach out to me. Thanks. Fade to black.